Have you ever pondered the complexities of three-dimensional spaces? If so, you're in good company. At the dawn of the 20th century, a French mathematician named Henri Poincaré found himself wrestling with a similar question. This led to the formulation of a proposition that would come to bear his name, the Poincaré Conjecture. For those who haven't tangled with this mathematical quandary, let's break it down. The Poincaré Conjecture revolves around the concept of three-dimensional spaces and something called topology. It's about the shape and structure of three-dimensional spheres. Imagine a three-dimensional space with no holes in it, a bit like a perfectly round balloon. The conjecture inquired whether every such space, known as a simply connected, closed three-manifold, is homeomorphic to a three-sphere. Now let's unpack this a bit. What does homeomorphic mean? Well, in the world of topology, homeomorphism is a kind of equivalence that preserves the basic shape of an object. Think of a donut and a coffee cup. While they might seem different at first glance, from the perspective of topology, they're the same as they both have one hole. But if we inflate that donut to a perfect round sphere without a hole, the scenario changes. The Poincaré Conjecture proposed that any three-dimensional space without any holes is essentially a sphere. This might seem like a simple proposition, but in actuality it was anything but. This conjecture was one of the most famous and challenging unsolved problems in mathematics for over a century. It was so significant that the Clay Mathematics Institute included it as one of the 7 Millennium Prize problems, offering a substantial monetary prize for its solution. So started the journey of the Poincaré Conjecture, an enigmatic puzzle that would stump mathematicians for over a century. As the 20th century unfolded, the Poincaré Conjecture remained a tantalizing mystery. This profound mathematical conundrum, proposed by French mathematician Henri Poincaré, had scholars scratching their heads and sharpening their pencils for over 100 years. The conjecture was elegantly simple to state, yet devilishly complex to solve. It revolved around the concept of three-dimensional spaces and topology, posing a fundamental question about the structure of three-dimensional spheres. The conjecture asked whether every simply connected, closed three-manifold is homeomorphic to a three-sphere. In layman's terms, it pondered if a three-dimensional space, devoid of any holes, is essentially the same as a sphere. This was a challenge of monumental proportions. The Poincaré Conjecture was known to be true for two-dimensional surfaces, but extending the result to the third dimension proved to be an entirely different beast. It became a mathematical Everest, a summit that many attempted to scale but found the climb too steep, the terrain too treacherous. The conjecture's perplexing nature did not go unnoticed. It caught the eye of the Clay Mathematics Institute, which included it in its 7 Millennium Prize problems. These were a collection of the most difficult unsolved problems in mathematics, and the institute offered a substantial monetary reward to anyone who could crack them. The Poincaré Conjecture, with its century-long history of defying solution, was a worthy inclusion. This added incentive did little to expedite a solution. The Poincaré Conjecture, with its intricate interplay of geometry and topology, continued to confound the best mathematical minds. It was a riddle wrapped in an enigma, a code that seemed unbreakable. Hundreds of minds tried to crack this code, yet the solution remained elusive. The Poincaré Conjecture, once a mere proposition, had become a symbol of the challenges and mysteries that lay at the heart of the mathematical world. As the century wore on, the question remained: who would finally decipher this century-long challenge? Enter the 21st century, a time of unprecedented technological advancements and mathematical breakthroughs. Amidst the bustle of this modern era, a quiet storm was brewing in the world of mathematics. A storm named Grigory Perelman, a Russian mathematician of formidable intellect and profound dedication. Perelman had set his sights on the Poincaré Conjecture, a problem that had vexed mathematicians for over a century. The conjecture was a tantalizing enigma, a question about the nature of three-dimensional spaces that had no clear answer. But Perelman was undeterred. He began his journey towards the solution with a deep dive into the works of Richard S. Hamilton, an American mathematician who had developed the theory of Ricci flow. This theory, which describes how the shape of a manifold changes over time, was the key that Perelman needed to unlock the mystery of the Poincaré Conjecture. With Hamilton's theory as his guide, Perelman ventured into the uncharted territories of the conjecture. He navigated its complexities with unerring precision, weaving together strands of mathematical logic into a tapestry of proof. And in 2003, he emerged from this mathematical labyrinth with a solution in hand. The Poincaré conjecture had been proved. Perelman's proof was a mathematical tour de force. It was a masterclass in the art of problem-solving, a testament to the power of perseverance and ingenuity. But it was more than just a solution to a problem. It was a beacon of hope, a signal to the world that even the most formidable mathematical challenges could be overcome. News of Perelman's accomplishment spread like wildfire. From the hallowed halls of academia to the bustling streets of the world's cities, people everywhere marveled at his achievement. The Poincaré conjecture, once an insurmountable obstacle, had been conquered. The mathematical community was quick to recognize Perelman's groundbreaking work. In 2006, he was awarded the Fields Medal, often dubbed the Nobel Prize of Mathematics. This prestigious award was a fitting tribute to Perelman's monumental achievement, a recognition of his contribution to the world of mathematics. But for Perelman, the real reward was not in accolades or prizes, but in the joy of discovery, the satisfaction of solving a problem that had stumped his predecessors for decades. He had cracked the code of the Poincaré conjecture, and in doing so, he had changed the face of mathematics forever. Perelman's proof was a triumph, transforming the Poincaré conjecture from a challenging problem to a proven theorem. His journey was marked by determination, innovation, and sheer mathematical brilliance. And his story serves as a reminder that in the world of mathematics, no problem is too great, no challenge too daunting, and no conjecture too elusive to be solved. It is a testament to the power of the human mind, the endless potential of mathematical exploration, and the boundless possibilities of the universe we live in. The resolution of the Poincaré conjecture was not the end of the story, but rather the beginning of a new chapter in mathematical research. When Russian mathematician Grigory Perelman solved the Poincaré conjecture in 2003, he didn't just solve a long-standing problem, he opened up a Pandora's box of possibilities, propelling the mathematical community into uncharted territories. The theorem's implications extend far beyond the realm of pure mathematics. Its proof has provided invaluable insights into the nature of three-dimensional spaces, reshaping our understanding of the universe's fundamental structure. More specifically, it has revolutionized the way we perceive the topology of three-dimensional spaces, the branch of mathematics concerned with the properties preserved under continuous transformations. In the world of physics, the Poincaré conjecture has found profound resonance. In particular, the fields of quantum physics and cosmology have greatly benefited from the insights provided by this groundbreaking theorem. It has shed new light on the nature of the universe, the fabric of space-time, and the fundamental laws that govern our reality. But the Poincaré conjecture's resolution has done more than just illuminate existing knowledge. It has paved the way for new areas of research and exploration. The theorem has given birth to a series of fresh conjectures and questions, each leading to new mathematical landscapes waiting to be discovered. One key area it has opened up is the study of Ricci flow, the mathematical tool that Perelman used to prove the conjecture. Ricci flow, a concept from the field of geometric analysis, has seen a surge of interest since the resolution of the Poincaré conjecture. It has become a vibrant and rapidly growing field of study, with potential applications in a variety of scientific disciplines. The Poincaré conjecture also underscores the power of collaboration and innovation in mathematics. It is a testament to the collective efforts of the mathematical community, from Henri Poincaré, who first formulated the conjecture, to Richard S. Hamilton, who developed the theory of Ricci flow, to Grigory Perelman, who finally proved the conjecture. It is a shining example of how collaboration, persistence, and creative thinking can overcome even the most formidable of challenges. In conclusion, the resolution of the Poincaré conjecture was a pivotal moment in mathematical history. It has not only solved a century-old problem, but also opened up new frontiers in our quest for knowledge. It has inspired countless mathematicians to push the boundaries of what is known and explore the infinite landscape of the unknown. The Poincaré conjecture, once an unsolved problem, now stands as a testament to human ingenuity and the endless possibilities of mathematical discovery.